Hello and welcome again to another edition of Lost in Science. This is half an hour on your radio or other listening device where we will talk about all things sciencey. Who are we? Well, I'm Stu, and on the show with me this week I have Chris.
Hey Stu.
Hi Chris, how you going?
Yeah, pretty good.
Have you got something sciencey for us this week?
Yes, I am talking about something that had the physics world a bit of a buzz a couple of weeks ago, which was a big announcement about gravitational waves. I don't know if you saw this. And this was a detection of ultra-low frequency gravitational waves by a collaboration called NanoGrav. That's the North American Nanohertz Observatory for Gravitational Waves. But it's not just North American, as I'll get into my story. But you're probably thinking, haven't we discovered gravitational waves before? Why is this such a big deal? Why are physicists getting excited over this again?
Again?
Yeah. And look, you're right. Look, back in 2015, there was a big discovery, a detection of waves from colliding black holes or neutron stars. This is different. This is very, very low frequency. As the name might suggest, sort of longer, slower waves, believed to be coming from pairs of supermassive black holes orbiting each other. Very different kinds of gravitational waves that have to be detected in a completely different way. When I say ultra-low frequency, that observatory, like I said, it had nanohertz in it. Now, when you think we normally do things in like from hertz to like kilohertz is what we can hear, this is like billionths of a hertz. We're talking like, oscillations once every few years.
The tiniest of hertz.
Yeah, we're talking like really, really slow waves. They're not slow, they move at the speed of light, but yeah, really kind of long, slow waves. Yeah, very, very, very low frequency.
Well, we'll have to get into that later in the show. And also, Claire is going to be talking to a guest from the Museum Victoria a senior manager of genetic resources, Jo Sumners, who's actually going to be on a panel at the Museum of Victoria on July 19th, if you're around, called The Genetic Rescue of Our Fantastic Beasts. But Claire is going to be talking to Jo about the earless dragon, which was sighted for the first time in half a century back in February and was thought to be extinct, but obviously isn't. I didn't know dragons had ears. Did you know that?
I did not know. That's my biggest question as well, Stu.
The distinction between an earless dragon and a dragon, I don't know if other dragons have ears or not, but I'm sure we'll find out. So that's coming up later in the show. Please stay tuned.
Yes, you're listening to Lost in Science, and once again, I find myself talking about gravitational wave detection. This time, the ultra-low frequency gravitational waves believed to be emitted from pairs of supermassive black holes. Now, I should probably start by talking a little bit about what gravitational waves actually are. Would that be a good starting point, you think?
I reckon that's as good a place as any to start.
Right.
Certainly.
So there are obviously... they are waves in the gravitational field, which is not actually a field. It is the actual bending of space-time itself. But I suppose an analogous thing here is like electromagnetic waves, which we might be familiar with. Things like radio waves and higher frequencies thereof. Now, electromagnetic waves are fairly well understood, but they're generally, I guess, in terms of classical theory, this is not quantum theory, produced by electric charges that are accelerating in some fashion.
Right.
So a radio antenna essentially is just a current that oscillates up and down the antenna, and then that gives off the radio waves, which are a form of electromagnetic wave. Pretty straightforward.
Yeah.
So when Einstein came up with his general theory of relativity, which gave us a good description of the way gravity works, it was natural to ask, could there be gravitational waves from accelerating masses? And the answer was soon calculated that yes, but again, these are not in a field, they are ripples in space-time they're described as, but they're also generally like very, very hard to detect. They're very not noticeable.
So you don't sort of get caught in the wash of a gravitational wave and suddenly feel heavier all of a sudden or anything like that?
No, and they are a form of energy that's given off by anything accelerating. So for instance, anything moving like say a planet going around the sun would be expected to give off gravitational waves. But again, it's so weak you wouldn't be able to feel it. But also the amount of energy it gives off in this fashion is so little that you're not going to notice a planet falling into the sun.
Right.
It's not enough energy to really make a big noticeable difference to the orbit.
Does it make a big difference if the things are bigger, if they're more massive?
Yeah, absolutely.
So the more massive something is,
yeah, absolutely,
the more of a wave.
And this is where we get to the discoveries in 2015, which was the LIGO observatory, which used laser interferometers to detect very minute changes in distance over a few kilometers. And that was from black holes colliding. Now, black holes are much heavier, obviously, than normal planets and other things like that. And when they're orbiting each other closely, they give off a lot of energy in the form of gravitational waves. So what you hear, you can convert this to sound essentially. What you get is this sound of, it's called a chirp, essentially. The black holes spin around each other faster and faster. They go faster and faster to get closer, and eventually they lose so much energy from these waves they're giving off that they crash into each other and they merge. And so that's what we've been used to detecting, are these collisions of black holes in this fashion. Like I said, anything that's not clashing like that should also give off gravitational waves. But again, it would have to be really, really big for you to detect it. And this is where we come to the idea that perhaps there are supermassive black holes that might give off detectable gravitational waves. Now, supermassive black holes are the things that are at the center of galaxies. You might remember fairly recently there have been pictures taken of the one at the center of our galaxy, as well as another distant galaxy. We've seen these things. They're millions to billions of times the mass of the sun.
Huge.
Yeah, and as far as we know, most galaxies have these things. Now, but we also know that galaxies come in different sizes, and it's believed that galaxies grow by merging, like two galaxies will combine. And when they do so, you'd expect their supermassive black holes to also merge. So there should be pairs of supermassive black holes that have merged galaxies that are orbiting each other, what they call binary systems. And they should be able to give off detectable gravitational waves. Except that these are going to be harder to detect because they're going to be very, very long wavelengths. We're talking a much slower orbit than these smaller black holes. And the oscillations, as I said in the introduction, will be on the order of years or decades. And the wavelength we're talking about will be light years long. You can't detect this with a laser observatory on Earth. You need something the size of the galaxy, essentially, to do so.
Do we have anything just lying around that we could use for that?
Fortunately, we do.
Amazing.
What they've done in this latest discovery, they've used pulsars. Now, pulsars are neutron stars, a special kind of rotating neutron star that gives off a radio beacon. And as it rotates, the beam rotates and you get this flashing beacon, and sometimes they rotate really rapidly, and you get these very rapid, very precise bursts of radio waves sent towards us. Now, this latest one has used millisecond pulsars. So these, I'm going to say milliseconds, that means they're rotating thousands of times per second. And like I said, they're super accurate clocks. What you can do is you can use variations in the timing that you're seeing of these pulses, because you know they're meant to be accurate. So if you see a change in the timing, then you can deduce that something has happened to the space between them and us. Okay, so basically when a wave hits the Earth, one of these large gravitational waves hits the Earth, it will bend the space around us, and it will change the time it takes for the pulses to get to us. It might only be in the form of like a few tens of meters of difference in distance to something that's like 1,000 light years away. But these clocks are so accurate that, it might be a few nanoseconds difference for it takes for the pulse to arrive, that we can detect that nanoseconds of differences. What they've done here is they've used a whole lot of different measurements of pulsars from across the sky, and so you see which ones are affected and if they're correlated and with having a particular direction, and you can work out whether there is these kind of waves causing these changes. Now, I should say the largest data set that they've used is actually from Australia. It's the Parkes Pulsar Timing Array, which is at the Murray Parkes Radio Telescope. They were able to use all these measurements from pulsars across the sky and detect yet that there is this discernible pattern of these changes caused by changes to space-time of these large waves washing over it. So I guess if you think of the normal waves detected before as kind of very kind of ripples in a pond, like something being dropped in a pond. We're talking here like ocean waves. We're talking like being in the open ocean and having waves coming in from different directions, these large waves that you don't know where they're coming from, but you bob up and down on those waves. And that's basically the Earth bobbing up and down on these, like a tiny boat on these light year long waves, if you want to think of it in that sense. They basically pretty much detected that there must be these gravitational waves here, and they believe they're from these supermassive black hole binaries because we believe they're out there. But the challenge will now to be to confirm that that's the case, to see whether they match the theory that predicts those waves, and also try and work out where specifically the waves are coming from, so that they can hopefully then turn this into another way of observing these galaxies as they collide.
Surf's up.
Yes.
Across Australia on the Community Radio Network, you're listening to Lost in Science.
So conservation stories don't get much better than the discovery of a species thought to be extinct, especially one that was thought to be extinct since the 1960s. And this happened in February this year with the rediscovery of the Victorian grassland earless dragon. Now, with me to discuss the conservation and groundbreaking biobank genetics efforts that go into saving the most endangered reptile in the world, we have Museum Victoria's Senior Manager of Genetic Resources, Dr. Jo Sumner. Jo, welcome to Lost in Science.
Thank you. It's lovely to be here.
Now, Jo, tell us a bit about the Victorian grassland earless dragon and how this species came to be rediscovered.
Well, it's sort of, I guess it's like the discovery of the unicorn of herpetology. So it was really exciting and one of those things that we dream about but weren't sure would ever happen. So this is a really cute little dragon. They only live a couple of years. They're quite small. They're found in grassland regions, and they live inside spider burrows. So they're actually not out and about very often, which I think is probably part of the reason why they've been so hard to find. They live inside, wolf spider burrows.
Wow.
At the beginning of this year, some ecologists were doing surveys out to the west of Melbourne and came across a lizard that clearly wasn't one that they expected to see there. And they had an inkling of what it might be and sent a few photographs to some ecologists that they knew, one of whom happened to be Peter Robertson, who literally wrote the book of Victorian reptiles. So once Peter saw it, he identified it and knew that it was something pretty amazing. And from there, a team was put together pretty quickly with Zoos Victoria leading the charge, because they have already had a captive breeding program up and running for the sister species of this dragon. So it all came together quite quickly. And what was quite astonishing was that there was already this amazing amount of expertise sort of ready and primed to go.
Wow.
Because the zoo had already been working with the Canberra grassland earless dragon. So up until about 4 years ago, this species, it was thought to be one species all through New South Wales, ACT and Victoria, and it was all known as Tympanocriptus pinguicola. So it was all grassland earless dragon.
That just rolls off your tongue. I love that.
I love a bit of Latin. But Dr. Jane Melville, who's the curator of herpetology at Museums Victoria, she had a look at the distribution across all these grasslands in Southeast Australia and looked at the genetics of the animals in that area and some of the morphology. So looking at the skull shape and the scale counts, and actually found that there were 4 species across this region. And so what we thought was a potentially extinct population of the grassland earless dragon in Victoria became a potentially extinct species of grassland earless dragon. So it kind of ramped up the importance of the species in Victoria. And in fact, all 4 of those species are critically endangered. And one of the other ones hasn't been seen since the 1980s.
So why is this particular group of lizards so threatened?
Because they live in grassland, native Australian grassland, and something like 99% of native grassland has been cleared mostly for agriculture. So it's lost its habitat because it looks like open, clear paddock. It kind of, some grassland looks a little bit scrappy. It hasn't been protected in the same way that native forests have. But it has a whole suite of endemic species that are also critically endangered. So we really need to save our last little patches of native grasslands and these gorgeous animals that you get in them.
So you talked a bit about sort of the captive breeding program that Zoos Victoria have in place for the Victorian grassland earless dragon. So what is the role of the museum in the conservation of the dragon?
I guess we've been leading all the genetic side of things. So there's a couple of different things we're doing. At the site where the dragons were first found, we did some swabbing around the spider burrows to see whether we can get some environmental DNA. So we're working to see if that's maybe another way we can identify other sites where the lizards might be. If we can't actually see them, maybe we can swab around and look for their DNA that's kind of, I guess, sloughed off when there's skin in the environment. So that's one stream that we're looking at. Another one is we've taken some tail tips from the lizards, because that's a really good way to get DNA without doing too much damage to the lizards. So we worked with Zoos Victoria on getting those tail tip samples, and that's allowed us to positively identify the dragons as the Victorian grassland earless dragon by comparing it with DNA that we've managed to get from some really old specimens in the museum. So this is one of the beautiful things about museums, is that we have this historical collection, and the technology for DNA work and DNA sequencing means that we can actually get DNA out of some really old specimens. So we were able to extract DNA from a specimen from the early last century and compare it to the DNA of these animals that were found recently, and match it up and say, yep, that is definitely the species that we think it is. And also with those tail tips, we're doing some other work, which is a bit like DNA fingerprinting. So we can have a look at the relationships among those animals. There's now 16 of them at Zoos Victoria. That's the beginning of the breeding program. We will be able to help them work out how best to manage that breeding population. I think there's only 4 females, so it's really, they have to be really careful in how they set up their breeding program. So we'll be able to look at the relationships between those animals using their DNA. The bit that I love and I think is the coolest and I'm most excited about is that over the last year, Museums Victoria have set up a live cell lab. So we have a tissue collection at the museum, which is held in the Ian Potter Australian Wildlife Biobank, and that we've got about 50,000 tissue samples from wildlife.
Wow.
So this is anytime somebody gets a scale or an ear clip or a feather or a toe snip from animals that they're doing research on, DNA research, we put those in our biobank and we freeze them down so that we can look at the DNA later. And researchers around the world can actually access the DNA and the tissue samples that we have in our biobank. But what we want to do is not just be able to look at the diversity that's there or even the genetic diversity as it's lost, but to actually have living cells in our biobank that we can then put that genetic diversity back into wild populations in the future.
A lot of our listeners would have heard of seed banks as a way of, I guess, holding on to precious genetic diversity. Maybe not so much have heard that that's an option with animals and with living tissues. So how is this possible?
Yeah, so I think the trick is making sure that the way you freeze cells is done so that the cells can then be thawed and are still alive. So normally if you stick something in the freezer, it gets ice crystals, and that actually happens inside the cells as well. So if you freeze something, you just whack it in the freezer, and our biobank goes down to minus 200 degrees.
Wow.
So it's really cold. Your normal freezer is only about minus 20. So it's much colder. If you can freeze things down in a specific medium and at a pace, a particular pace, then those crystals won't form, and then they won't split open the cells as they form. So what you get is a cell that can then be thawed out again, slowly and carefully in a particular way, so that the cells are alive again when you thaw them out. And you can do this with a whole range of different cells. So you can do it. This is like IVF in some ways. So
Yeah.
you can freeze sperm. So in fact, we've been again working with Zoos Victoria, and we've got sperm samples from their frog breeding programs. So we also have some of those frog samples and the genetic diversity that is in those samples now in our biobank, so that when the zoos program, if they need diversity that's found in one of those animals and they want that back into their breeding program, then they'll be able to access. And so that's one part of what we do. But the one that we've been working on, and that is pretty cool, is actually growing cells from skin. So these are called fibroblasts. So the initial program that we were looking at was growing live cells from ear snips from mammals. So little antechinus, sort of the small marsupials, but also some native Australian rodents as well. And by growing those cells, we can grow enough that we can then freeze those cells down. And the hope is that by having those living cells in our biobank, in the future, we'll be able to change those into something called a pluripotent stem cell, or an IPSI cell. And those cells then have the capacity to be changed into any other cell type. So
does that
include a gamete? So
that includes gametes?
Yeah, that includes
eggs
gametes.
or sperm.
Eggs or sperm. So that's sort of the pathway.
Wow.
That we can use living cells that we grow from an ear snip of a native mammal, or the tail tip of a Victorian grassland Illis dragon.
Wow.
And then by growing those cells, we can then, in the future, researchers hopefully will be able to transfer those, change them into IPSI cells, and then back into gametes. And then those gametes can be put back into the wild populations. But unless we start now and we actually bank down the genetic diversity that is available in populations now, then we won't have the same diversity and opportunities to put that back in the future. So even though we don't have all the technologies down now, we really, really need to bank as much genetic diversity down in our biobank now as we possibly can.
We're not going to get any more genetic diversity as we go along.
Well, we do. I mean, that's what evolution does, is it builds it. But what's happening at the moment is that we're losing populations so quickly, and with climate change, we need it can't keep up. Evolution can't keep up with the changes that are occurring. So we've got to try and give it a little helping hand by holding on to some of the diversity that we have.
It's a forward-focused and fascinating technological initiative. Are there any limitations to the biobank? I mean, apart from the fact that the pluripotency research isn't exactly where we want it at the moment?
I think there's lots. It takes, I think every species is a little bit different in what it needs and how we grow the medium that they need to grow in the first place, and then exactly how to freeze them down. So it's likely that we have to do it species by species and do a little bit of tweaking with everything. So it can be quite a slow process, but we need to start. And we've already got I think 74 vials of living cells in our biobank from this last 12 months of work with mammals, and we've got 2 dragon species and an albatross and a brolga as well. So those ones are just ones that were I think they were taken to Zoos Victoria, to the vets, because they'd been brought in by wildlife carers, and they unfortunately didn't make it. They both died. So then they were given to the museum, and as a museum we want to maximize all the possible uses that we can have with those specimens, because they're so rare. So one of the things we did was we tried to grow some cells from them, and we were successful because we have this lab set up and we're ready to go, and really looking forward to having, making those opportunities where they are.
And is this the first of its kind in Australia?
Yes, it is. Melbourne Museum is the only museum in Australia that has a biobank. So there's other museums that that have a frozen tissue collection, but they keep those in sort of -80 mechanical freezers. What we have is this liquid nitrogen cryo storage facility. So that's the only way you can keep cells at the temperature that's low enough to preserve them into the future. It's a temperature that stops all biological activity. So they are just in stasis until we are ready to bring those cells back again. So yeah, and we're the only museum as well that has this cell lab, this live cell facility, which is pretty exciting.
It's incredibly exciting. What's next for conservation efforts and genetic research for the Victorian grasslands Aeolus dragon?
One really cool piece of work that we are able to do, because we have those cells growing, those live cells growing, is we're able to sequence the entire genome of this animal, and that's going to give us all sorts of information that will help with the ongoing conservation of the species. So it's a bit of a dream come true that we've been able to get from a potentially extinct animal to a conservation program and having the entire genome sequenced in about 6 months. So I'm really thrilled that we're able to do that.
That's so exciting. And I imagine once that genome is sequenced and published, then, it opens the door for so many other researchers and scientists to be able to do further work and conservation genetics on that species.
Absolutely. And we work with a whole slew of researchers, and all this information becomes publicly available, because it's really important that that research is available, and this kind of data is available for any researchers.
Jo, you'll be speaking on a panel this week about the conservation efforts of Museums Victoria, the Victorian Aeolus dragon, and the biobank. Can you tell us a little bit more about that?
Yeah. So this is part of Museums Victoria's Future Forums, and this particular one is called The Genetic Rescue of Our Fantastic Beasts. So it's kind of been done in conjunction with one of the exhibitions we've got on about fantastic beasts, which is come over from London, and it's sort of looking at the Fantastic Beasts Harry Potter world, and some of the extraordinary beasts that we have in real life. So I guess we're looking at how we conserve our own fantastic beasts. Yeah, it should be really good. So people can either log on online or come in person. And if you come in person, then you can go down and see the exhibition as well.
And who will be joining you on the panel?
So we'll have Natasha Mitchell there from ABC Radio National. She's going to be the moderator, and also Marissa Parrott from Zoos Victoria. And we've got an international guest as well, Professor Anne Mugai, who's a professor of genetics and has done extraordinary work a lot with over the agriculture and genetics of animals in Kenya and throughout Africa. So it's a really nice balanced panel. It should be really, really interesting. I'm excited.
Well, Jo, thank you so much for speaking to us today about the Aeolus dragon, the biobank, your work. It's incredibly important and, very exciting as well. What a wonderful story of conservation, and best of luck, and look forward to hearing the panel.
Thank you so much.
That's all we've got time for on this episode of Lost in Science. Thanks for tuning in and joining us. Lost in Science is recorded at the studios of 3CR in Melbourne and broadcast across Australia on the Community Radio Network. If you want to talk to us, you can get in touch. We have a Gmail account, lostinsight@gmail. You can also find us on Twitter and on the Facebook. And if that's not enough Lost in Science for you, you can always tune in again next week, where the team will once again get lost in science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.